Okay, hello weasels. I hope you're doing well, and I hope you're behaving. Everybody have their notes out and ready to go? Okay, if I go too fast, please let the sub know and she'll pause the video and you can catch up. You shouldn't have any homework to turn in, so it's just straight to notes. Let's go. So, this is set 122, permutations. Permutations. First of all, it's hard to solve a permutation problem if you don't know what a permutation is. So get this down in your notes. A permutation is a way to order two or more. I'll just say things. They might be letters, they might be numbers, they might be people in a seating chart. There's lots of different permutation problems. It's a very common real life kind of problem, right? There are two ways to count permutations. One is to count all possibilities just by making with an organized list. I'll use a tree diagram. Okay, it's a visual way to do all the different possibilities without just thinking of them, which always involves missing one, okay? So it's a way to organize all the different possibilities. Two is a shortcut. I'll call the fundamental counting principle, which is a bit of a mouthful, so I'll just call it, I don't want to tell you how to do it yet. That's the shortcut. You got to pay your dues first, all right? So we'll get to the shortcut in a minute. Let's start with the tree diagram. Don't worry about that second part of your notes. How many ways? Actually, a tree diagram. Let's go to understanding the shortcut of where it comes from, but first with the tree diagram. Now, I'm going to sit Al, Bob, and Claire, A, B, and C for short, in a row. Now, I could start just making a list. A, B, C, A, C, B. But almost inevitably, especially when you're dealing with big sets, things get forgotten. And so you have to have an organized way of knowing what have you done, what haven't you done. That's what a tree diagram is for. So the first thing you're going to do is vertically put all the possibilities for the first seed. Now that could be A, leave yourself a little space, then B, then C. Now at that point then, in that first space, you had three choices. With me? Now the bottom will be where the shortcut comes in. Now let's consider all the possibilities of if I sat Al in the first seat. If Al was in the first seat and I went to do the second seat, and I could actually go two different ways. I could go either Bob in the second seat, which would then mean Claire would have to be in the third seat. So that arrangement would be A, B, C. Or, after sitting Al, I could go Claire in the second seat, and then Bob in the third seat. That would be A, C, B. Now, if I put Bob in the first seat, then I could go Al in the second seat, and then Claire would be seated. Or if Bob is in the first seat, I could go Claire in the second seat, and then Al. That would be BAC or BCA. And then finally, if Claire was in the first seat, I could go Al next, then Bob, or Bob next, then Al. That would mean Claire, Al, Bob, or Claire, Bob, Al. But at that point then, I am out of different arrangements. There is no new arrangement after I've done all those. So the shortcut then is I have 3 choices for the first movement. After that, off of each of those, I multiply each of those by 2 choices. Each of those branched off to 2 choices in the second seat. But after I had sat 2 people, then in the last seat, I only had 1 choice. Last seat or third seat. Now then, given that there are 6 possible arrangements, what must we do with these choices for the shortcut? Did I add them or multiply them? Well, doggone it, this is a really terrible example because they both had the 6. Terrible, but I'll tell you what, I should have done 4 so you can see there's a difference. It's multiply. You multiply the different possibilities. So the shortcut then for counting permutations is you put a space down for every choice to be made. I'll explain more in a second there. And then you put a number in each space to represent how many choices. And then what you do with those numbers is you multiply. Now this seems pretty simple and straightforward, but this is actually a huge source of higher level math called combinatorics. This, in fancy pants language, is the fundamental counting principle. But the idea is what's important, not the name. I don't care if you know the name fundamental counting principle. So let's just use the shortcut. The tree diagram is a great fallback if you get confused. But the shortcut's your first thing you want to try. I had this as example 3, but I think it's example 2, isn't it? Yeah. Okay, so we'll call this example 2. How many ways can the letters of I love math be arranged? I love math. Yes, I know you do. All right, so get the question down. I'm sure there's lots of agreement right now in class. Yes, that's definitely me. I'm sure Logan and Santi are saying it right now. Maybe Aaron, Matt. Okay. Here we go. Now, using the shortcut, let's first, I'm going to arrange all these. So there are 1, 2, 3, 4, 5, 6, 7, 8, 9 different letters to arrange or rearrange. So I'm going to put down 9 spaces. 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, in the first space, I could put an I, an L, an O, a V, an E, an M, a T, an H. I have 9 choices. Now, part of these questions they will tell you, can you reuse a letter or not? Usually that said repetition or repeating a letter is or is not permitted. I'll say repetition is not permitted. You cannot reuse a number, right? Now, if I just used one of my letters here, then for the next space, I only have 8 choices. And now I've used 2, so the next space I only have 7. When I've used 3, I only have 6 letters, then 5, 4, 3, 2, and 1. So I put spaces. I put how many different choices can be made in each of those spaces, and you multiply. Now you actually do this so much that there's a notation for this to shorten it up. The notation is this. Maybe you know it. It's 9 with an exclamation point after it, and it's read as 9 factorial. It doesn't really mean 9 with emphasis, like 9. It's 9 factorial, right? If you wanted to multiply that out, you can. It gets a little gross after a while. This is 2, 6, 24, 120, 720. Then you're talking more like 5,040, and then 4,320, and by the time 40,320, sorry. And by the time you hit to 9, you're in the 360,000-ish kind of range. Don't worry about multiplying that out. I just want you to understand. You with me so far? Okay, now, what if you only take a subset? Sometimes this happens. How many different 3-letter combinations from the 9-letter I Love Math choice pool can be made? I'll give you a second to write that down. Okay, so that shortcut is going to be used. Now, how many spaces do we have to put down? Well, I'm making 3 choices. I'm going to put a letter, and a letter. 3-letter combinations. So because I'm only doing 3-letter combinations, that means I'm only using 3 spaces. For the first letter, though, I still have 1, 2, 3, 4, 5, 6, 7, 8, 9 different choices. So I have 9 numbers to choose, letters to choose from. Now, assuming again I say no repetition, then I'll have only 8 choices and then 7 choices. And then once I've filled those 2 spaces, then I'm just done. The other 6 letters just don't get used. They're just hanging off to the side. And I multiply. Now, that doesn't have a factorial notation. It doesn't. Factorial means 9 times all the numbers, all whole numbers beneath it till 1. Now this is not 9 times all the whole numbers beneath it till 1, so you wouldn't use a factorial here. You would just multiply. 8 times 7 is 56 times 9 is 504. There are 504 different ways to take 3 letters from I Love Math and make an arrangement. And you can see why you don't do the tree diagram for this type of case, because that would be a lot of branches to the tree, yeah? Okay, let's try one more kind of real-lifey problem. One more example after that. Sorry, this should have been, this was example 3. This is example 3. This will be example 4. Okay. How many different locker combinations are possible? No repetition of numbers. All right. Get that down. Feel free to abbreviate a little. It doesn't have to be verbatim or word for word. Now, locker combinations have 3 numbers to them, yeah? So because of that, we're going to order 3 different things. On your locker, how many different numbers are there? Did you see that? It goes from 0 to 49. How many numbers are there from 0 to 49, including 0? Is it 49 or is it 50? It's 50. Okay, so you have 50 choices for your first number. in the next, you can't use the same number because you wouldn't, well, I guess it depends on the lock, but it's not common, at least not on our lockers, that the same number happens twice in a row. So no repetition is permitted. The next is 49 choices, then 48 choices. That then is a lot of combinations. If I do 49 by 48, you better be doing this yourself. Take 49 by 48, and let's see what we get there. I get 2,312 there. Do you agree? Now we're going to multiply that by 50. I'll multiply it by 5 and add a 0. Altogether then, we'd have enough combinations to have 115,000 students have different combinations. So these numbers grow really fast. It's really big growth. There's different kinds of growth in math. Linear growth is kind of proportional. It's kind of slow. Factorial growth is really quick. In calculus, you'll talk about rate of change. It's a big deal, okay? I think we're good. I talked about factorial notation, so just so we're clear, let's jump down to this example, which is example 5. Example 5. What does 4 factorial equal? 4 factorial means 4 times all the numbers beneath it until you get to 1, yeah? 4 times 3 times 2 times 1 is 12 times 2, or 24. Okay? All right. Try these 2 practice problems to see if you get the gist on your own. We'll go over them after you've practiced them, and then the sub will hand out the homework. You do not have to write the problem now. You can just do the question. I spelled characters wrong. What the heck? Sorry about that. When I say digits, that means number symbols. How many number symbols are there? If we include 0, although some license plates don't include 0 because it looks like an O, but I'll include 0. You should be working this problem, not waiting for somebody to do it for you, including multiplying. Now you can now use your calculator or your phone. Okay, so let's check. You've got a license plate with 4 characters, which actually in real life it's more characters unless you go to a really small state with not many people. How many letters are there in the alphabet? Please tell me you know that. Okay, 26. If it says repetition is permitted, which is to say, even if I used an A in the first spot, I could also use an A in the second spot. Then did I use up a choice, or can I still have 26 choices for the next? And I hope you're saying I still have 26 choices. After that, we're talking digits. So 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. That is 10 choices. And again, because repetition is permitted, I could use a number twice, like 3, 3 or 4, 4. And I still have 10 choices there. So I just need to multiply 26 by 26 and add 2 zeros is the shortcut. So if I do that, I get 676 with 2 zeros. So this state would have to be very small, 67,600 plates. Whee! All right, last one. Which is bigger? 5 factorial, that's red, or 5 cubed? Okay, so let's go, see how you did. 5 factorial is, there are a lot of ways to group this. I like 5s and 2s together. And so that's 120, yeah? 5 cubed does not mean 15. Please don't make me throw up. That means 5 times 5 times 5, which is 125. So we conclude that 5 cubed is bigger. Okay, now if you would get out your book and the sub will hand out the problem sets, you're going to turn to page 122. Work for the rest of the period. Mrs. Bender, if the kids want to come up and check their even answers with the answer book on the desk, I let them do that, and that's fine. The 8th graders like to wander around a little bit and get out of their seats. Definitely that's a no. They should just sit there and do their work, and hopefully they will make it productive. Okay? Thank you and have a good day. I'll see you guys soon. My plan is to be back Wednesday.